Hello, we are the bicycle analysis group in Mech Design 2. Today we'll be analyzing the GTX3 bicycle, and this image is from Dick's Sporting Goods. So the work division, theory of operation, we all contributed to that. The chain drive and analysis was done by Case. Brake analysis was done by myself and Ryan, and the rear wheel shaft was done by Lucas.
So first, we're going to talk about a little bit of the theory of the operation of the bicycle itself in general. The bicycle is a machine that converts human effort to turn two wheels and move people forward. The overarching components of the bicycle include the frame, tires, driving gears, train, and the braking system. So we wanted to talk about a little bit more of the power flow that happens within a bicycle to allow for a linear motion to take place. So first is the human power input into the pedals themselves. People have to continuously press down on the pedals to make them rotate in the manner you see on the right. And this pedal motion is turned into an angular velocity through the power of the torque and is transferred through the chain rings into the back of the wheel to make the wheel spin.
So once these wheels are spinning, the whole system can move forward. And then another power flow or reduction of power is the friction of the wheels hitting the ground, like the rubber on the asphalt, and also the braking system, which intentionally decelerates the system.
For theory of operation, we divided the bike up into like just three like generic parts. So we have we have the chain drive, and then we have the brakes, which are going to be the part that I'll analyze. And then we have the rear wheel axle.
We'll begin by analyzing the chain drive of the bicycle. So a chain and sprockets, or also known as chain rings in a bicycle, are utilized to transfer applied force at the pedal to the rear wheel. A series of chain rings form a cassette at both the front and rear of the bicycle to provide multiple gear ratios. And a chain derailleur is used to move the chain between these chain rings. Begin with measured dimensions of the chain of the bike that we analyzed. Begin with the width between the plates of the chain was 11/128 of an inch. Seems odd, but that's actually a standard. Outer width, so the total outer width from the outside edge of the plates was 9/32 of an inch. The pitch is the distance between the rollers of the chain, was measured to be 1/2 inch with a roller diameter of 5/16 of an inch. The chain ring dimensions, we will be analyzing the highest and lowest gear chain ratios of this bicycle. So we'll begin with the largest chain ring on the rear wheel at an outer diameter of 4.5 inches, 28 teeth, a pitch angle of roughly a little under 13 degrees, and a pitch diameter of 4.47 inches. And then the smallest chain ring on the rear wheel at an outer diameter of 2.25 inches, 14 teeth, a much larger pitch angle of 25.7 degrees and a smaller pitch diameter of 2.2 inches. Moving towards the front by the pedals, the largest front chain ring had an outer diameter of 7.75 inches. It was 48 teeth with a pitch angle of 7.5 degrees and pitch diameter of 7.65 inches. And then the smallest front chain ring had an outer diameter of 4.5 inches, 28 teeth. Again, the same pitch angle as the other 28 tooth sprocket found in the rear, and the same pitch diameter as well. The goals of this chain drive analysis were to classify the chain and also determine and compare failure modes of the chain when operating at low and high speeds. Begin with the chain number. A bicycle chain dimensions do not exactly align with the ANSI standards, but we'll notice that this chain is very similar to an ANSI 40 chain with a smaller width. And this is due to the fact that this bicycle uses a derailleur to move between multiple gear ratios, multiple chain rings, so that the chain dimensions must be thin enough to not interfere with this operation. To analyze the failure modes, as previously stated, we'll study a low speed high torque ratio and compare it to a high speed low torque ratio. Beginning with the low speed high torque ratio, a large front sprocket will drive a small rear sprocket or chain ring. And in this case, the gear ratio was 48 in the front and 14 in the rear. And for this analysis, we will assume that the bicycle is traveling at 10 miles an hour. And for the high speed low torque ratio, a smaller front sprocket drives a larger rear sprocket. In the case of this bicycle, the chain rings are actually the same size, so the gear ratio is 1. And we will assume that the bicycle is traveling at 25 miles per hour. To study the failure modes, we utilize the above equations found in the Shigley textbook and the lecture slides to determine the failure mode of the chain in each scenario, and then utilize the definition of power to relate allowable power to maximum allowable input force at the pedals. To conclude, when the bicycle is operating at a low speed, it is link plate limited with an allowable power of 38 horsepower. And to transfer this to a little bit more palatable understanding, an allowable input force at the pedal of 911 pound force, which is quite high. And when operating high speed, it is still link plate limited with a smaller allowable power of 22.6 horsepower and allowable input force of 216 pound force. So in this bicycle, the chain is link plate limited when operating at both low and high speeds, and wear and improper lubrication are far more likely to contribute to failure than simply input force alone.
To start on the brake analysis, the brakes that our bicycle that we used analyzed is linear pull or V brakes, which just like most just clamp onto both sides of the rim and squeeze together to provide friction to the wheel. V brakes, there's multiple types of brakes to be used. V brakes are the most common in cheaper sold bicycles as they're easier to adjust and they provide a lot of force when squeezing, and it's a low rate of failure relative to ones that have to be manually adjusted.
And right here we have just like basically two free body diagrams showing like kind of how like the forces are kind of how the forces are. So on the left of the screen you have the side view of the brake lever or the fulcrum. So basically the part that the brake pad that actually like goes onto the wheels. Only one side, doesn't show both of them. It's just analyzing like one side of the brake pad. And in it you have force, the pulling force, which is like applied, which is pulling at the very end of the pad from the pivot point of the low arm. And I labeled that whole length as length A. And then the actual brake pad, the distance from the brake pad to the pivot point, I labeled that as length B. And And then through some calculations, I took the moment of like the full arm and then took that moment divided by the length of like the distance between brake pad and the pivot point to get like the actual force applied onto the tire itself for one of the brake pads. And then on the side view of the tire, there's just like a diagram showing the whole tire itself. This kind of so we in this I assume like the force and normal force the applied force is going into the page since we're looking directly like at the tire from the side view. And from there I calculate I just assume the normal force was the same as the applied force, which is why I have it equalized there. And from there I got to calculate the force of friction being applied to the tire. And from there you can calculate the amount of torque that this force of friction is applying to the tire itself using the radius of the tire and all that.
So for our brake analysis, we modeled them as disc brakes, even though they are not. But it's similar enough in concept to our lecture slides that it still applies. So the brakes are slowly squeezed together to slow the tire rotation down. And they can be modeled as an external shoe, like in the lecture slides, with the torque equaling the normal force applied times the friction constant multiplied by the radius of the tire. We can assume the brake pad and rim material as rubber and aluminum. So they have a mu value of 0.76. The total contact area of the brake we assumed as just a rectangle. There are small nuances to it, but they're more than likely insignificant to the overall action of it, as 660 millimeters squared. And the force applied by each hand squeeze. So with the left hand squeeze going to either the front or rear and the right going to the front or rear, one squeeze pulls both of these levers together to act on the tire. So the overall braking efficiency can be shown as the force of the front brake plus the force of the back brake equaling the mass times acceleration, or in our case, the deceleration. For this, we initially assumed no other losses in the system. That way we could just analyze the brake themselves.
And then and here are the actual calculations for the whole process. So from the measurements, we got the brake. So like that's what dimensions of the brakes, like the exact measurements, it's like lengthwise is 59.69 millimeters long, and then widthwise is 11.39 millimeters. So we got the total area to be 679 millimeters squared, and then the muted rubbers. And then for grip force, we assume from some little research, we assume that the force being applied to the brakes is around like 6 kilograms of force, which is like about the average that you would apply to like natural handbrake when you like squeeze on it.
I guess
And then
we should specify the average hand grip could be more, but that's like the max that would activate 100% of the braking force for us. So
yeah,
it's the maximum that we need to actually analyze for.
yeah, that's more accurate. Thank you. And then of course we have the measurements shown before, and from the calculations, the equation I mentioned a few slides ago, the applied force came out to be about 179 newtons, and with the force of friction and with the mu applied to it, the force of friction was 136 newtons. And when you multiply that and then working with the radius given in millimeters, you get, or in meters, sorry about that, the torque comes out to be 96.67 newtons meters. And when you multiply that, or you don't know the torque, I'm sorry about that. And then for the total pressure applied to the actual brake from like the pad itself came out to be 0.1219 pascals, which is just like which is like the force applied over the area of the pad itself. All right, and then here we have the rest of the values. We have and since there were like our total of 4 brake pads throughout the bike, like 2 in the front, 2 in the back, we just assume they all give out very similar like forces, like distributed equally. Obviously, that's not like very realistic, but that's kind of something we had to make it work. So we multiply all the units by 4, and then so the total newtons throughout the bike for like force applied came out to be 717,621 newtons, and then for friction 545, torque 387, and then for total pressure 0.4878 pascals. And then when we're analyzing the speed of the bike itself moving, we assume that the speed of the person was going at was 12 miles per hour. And so when we convert that into meters per second, which came out to be 5.636 meters per second. And then we got the diameter of the wheel, which came out to be 0.7112 meters. Wheel circumference calculated becomes 2.234 meters. And then using the speed of the rider, we use that as the tangential velocity, and we use that to calculate the rotational velocity or the angular velocity of the wheel itself, which we converted into rotations per minute. And then we got 143 RPM. And then we assumed the total mass of the bike and the rider itself to be 869 newtons. And so we calculate and we use the simple force equation from earlier to calculate the deceleration from the bike, which was 1.25 meters per second squared. And we also consider the deceleration from asphalt, which came out a little bit to be 0.196 meters per second squared. So total deceleration was 1.45 meters per second squared. And then using that, we calculate the average time to stop, which came out just be around 3.69 seconds. Yeah, a lot of numbers.
So now we're gonna be talking more about the rear wheel axle. And the axles are one of the most important components of the bike, along with the other components we've talked about. They support both the rider and the bike itself, and it contains one of the main things is a wheel hub assembly that includes a bearing that allows the wheel to spin freely. So first we need to talk about how to conduct a force analysis on this axle. I wanted to learn the components of the axle, including the measurements and the material analysis of what this axle could be made out of. I wanted to create logical assumptions of how the weight of the bike and its rider are distributed between the front and the back wheels, so I could talk about one specific axle, such as the rear wheel one that I will be talking about. And so we have to calculate the force on supports due to the acceleration due to pedaling and the deceleration due to friction as well. So these are some of the necessary assumptions I needed to make to continue with my analysis. So the bike and the rider would weigh 869 newtons about. The bike accelerating was at a rate of 0.13 Gs. The bike's frictional acceleration was at a negative 0.02 Gs because I found some information of that kind of acceleration when the bike was traveling on asphalt. I assumed the axle material to be of a durable 4130 structural steel, which I found from information online. And the idealized wheel hub assembly was had a consistent diameter of 28.58 millimeters over its 107 millimeter length. So these are some of the measurements for the shaft itself. The axle itself. The axle was made up of a nut, a spacer, a wheel hub assembly, and another nut and spacer on the opposite side of it as well. Here are some of the lengths and widths that I measured from these shafts, and I also modeled the axle in SolidWorks for easy access. Here are some of the one of the free body diagrams for the entire axle itself. You can see that there are on the sides, where it's bolted into the bike is where it takes half of the force of the weight and half of the force of the total acceleration in general on both sides. And then the reaction forces are found in the middle where the bearing is holding the actual wheel itself. Here are the XY plane shear and bending moments of the axle itself. And you can see that on the sides, it is holding about 260 newtons and meeting in the middle to create a large bending moment in the middle of the axle itself of about 24 Newton meters. Similarly, this is the XZ plane shear and bending moment diagrams that I constructed. On the sides, the acceleration was creating a force of about 47.8 newtons and meeting in the middle once again to create a max bending moment at point B in the middle of the axle of about 4.4 Newton meters. So using that information, I could find the point of max bending moment, which is of course at the middle of the axle, since both max bending moments were at the middle of the axle as well, for a total max bending moment of 24.4 Newton meters. With our assumption that the axle was made out of 4130 structural steel, we can find the yield strength of that to be around 689.476 megapascals. Using bending moment equations, I was able to find a bending moment stress of about 10.65 megapascals. And this was idealized with the wheel hub assembly having a diameter of 28.58 millimeters of that 4130 structural steel. And using those numbers, I was able to find a factor of safety against a yielding failure for that wheel hub assembly of about 64.74 in our use case scenario that was described earlier. Thank you, and I hope you enjoyed this technical presentation on our bicycle.